Hello everyone, my name is Awais Akhtar and I am here to present my BTech project on the topic Recursive Least Squares Algorithm, a study on forgetting factors. Let's have a look at the index of my BTech project. First we will discuss the introduction and related works on Recursive Least Squares algorithm. Then we will discuss the Recursive Least Squares algorithm and compare it with the Kalman filters to see what are the difference in the results. We will also discuss the variations in the recursive least squares algorithm by using multiple techniques such as robust variable forgetting factor, transversal filters, ladder estimation, and kernel recursive least squares algorithm. Lastly, we will discuss the important results and conclusion of the project. Recursive least squares is a well-known adaptive filtering algorithm that effectively updates the recorded historical data based on the new data, and the past data is discontinued by a forgetting factor. In BTP1, we discussed an adaptive algorithm which prioritizes the most recent samples as well as nearby samples to solve both time varying and non-linearity problems. This project aims to explore and implement the recursive least squares algorithm for estimating unknown parameters in signal processing applications by discussing the various methods of handling the forgetting factor of the algorithm. We will focus on understanding the theoretical foundations of the algorithm and its practical implementation in Python. Let's have a look at the online adaptation of soft sensors. First, we will have an historical input data in our modeling technique along with the output data. Then, by using our sensors, we will make predictions, and we will use these predictions in an updating strategy which uses the online input data to help the soft sensor make new predictions. Let's have a look at the related works on this field. Wang et al. Proposed an optimized version of moving filter principal component analysis called fast moving window principal component analysis, FMWPCA. Adaptation of non-linear models has also been reported in the literature. Lee et al. Proposed a moving window kernel PCA. Lee et al. Proposed a recursive non-linear partial least squares algorithm to solve both non-linearity and time varying issues encountered in the modeling process. Just-in-time approach is a local learning method. The time varying issue cannot be solved unless an adaptive mechanism is introduced into the just-in-time framework. Recursive least squares can be considered as the recursive equivalent of standard least squares algorithm. In RLS, a single new data point is analyzed in each algorithm to improve the estimation of the model parameters. We use the Sherman-Woodbury formula to avoid computing matrix inversions at each iteration step. It is important to note that the aim is not to minimize the overall mean squared error like for least mean squared. Hence, recursive least squares tend to much faster convergence but has a higher computation cost. We also define a forgetting factor lambda in order to define how much weight to give to the past input data. Let's have a look at the comparison between Kalman filters and recursive least squares algorithm. Kalman filters is a probabilistic algorithm used for state estimation, whereas recursive least squares is a deterministic algorithm used for parameter estimation. Kalman filter uses Bayesian probability theory to estimate the state of a system, whereas RLS uses linear regression to estimate the parameter of a system. Let's have a look at the formulas used in both the algorithms. Kalman filters is an optimal in the sense that it provides the best linear unbiased estimate BLUE of the state given the available measurements and knowledge of the system model, whereas RLS is not optimal, but it converges much faster than Kalman filter for certain problems. Kalman filter is also known commonly used in control systems, navigation, signal processing applications, where the goal is to estimate the state of a dynamic model. But recursive least squares is used for system identification and adaptive filtering, where the goal is to estimate the parameters of the system that is changing over time. Kalman filter requires storing the state estimate and covariance matrix at each time step, which can be computationally expensive for large systems, whereas recursive least squares only require storing the inverse of the correlation matrix. These are the results of applying recursive least squares algorithm on daily demand forecasting dataset. Whereas these are the predictions made by the Kalman filters. Let's have a look at the different variations of uh, in the forgetting factor and in the algorithm of recursive least squares. Robert variable forgetting factor. In this implementation, we set the minimum and maximum values for the forgetting factors. We choose a robustness parameter that controls how fast the forgetting factor can adapt to changes in the input data. Delta is a small positive number added to the diagonal of a covariance matrix to avoid numerical issues. This function returns the estimate coefficient with shape m and covariance matrix P of the estimated coefficients with the shape m, m. Let's have a look at the results of applying robust variable forgetting factor on daily demand forecasting data. Let's understand the transversal filters for adaptive filtering. In this implementation, we set the minimum and the maximum values of the forgetting factors. Transverse filters are designed to adapt changing the input signals in real time by updating the coefficient based on the current input and output signals. The recursive least squares incorporates a least squares error minimalization criteria, which ensures that the filter coefficients are optimized to minimize error between the desired output and actual output. This leads to more accurate and reliable filtering process. In this process, we define a smoothing parameter that controls the speed of adaptation along with the filter order. The, the function returns the estimated filter coefficient W with the shape order comma and the coefficient matrix P of the estimated coefficients with the shape P order. Let's have a look at the results produced by applying traversal filters for adaptive filtering on daily demand forecasting dataset. Kernel recursive least squares algorithm. The KRLS uses kernel function to map the input data into higher dimensional feature space. In this feature space, the data is expected to be more linearly separable. The algorithm estimates the regression function by iteratively updating a set of weights that define a linear combination of the mapped input data. The weights are updated in a recursive manner where each update depends on the current estimate of the regression function and the current input data. The algorithm works by maintaining a set of basis functions that span this feature space. At each iteration, the algorithm selects a new basis function that is most informative with respect to the current input data. The algorithm is also computationally efficient and it can handle large datasets and high dimensional input data. The gamma parameter controls the kernel width and the n components parameter control the number of basis functions and the alpha parameter controls the regularization strength. Implementation of kernel recursive least squares algorithm. Let's have a look at the ladder estimation algorithm on recursive least squares. Ladder estimation algorithms are a class of adaptive filtering algorithms used to estimate the parameters of a linear dynamic system in a recursive manner. The algorithm uses ladder structure to solve the linear equations, which allows for fast and efficient computation of the parameters. The ladder structure is found by cascading a series of RLS filters, each with decreasing forgetting factor. The forgetting factor determines how quickly the algorithm forgets old data and adapts to a new data. It has fast convergence properties and it is numerically stable even when dealing with ill-conditioned matrices. It also has low computation complexity, making it suitable for real-time applications. Implementation of ladder estimation. Recursive just-in-time model. The goal of the recursive least squares algorithm is to accommodate the latest data point x, y into the estimation of the model coefficients. For recursive least squares, the most important step is to assign appropriate weights to covariance by putting a forgetting factor on the past data. This is done in the following way, where we apply lambda parameter to the old parameters and add the new input data. Uh, these are the results produced by the implementation of recursive least squares, a recursive just-in-time model on the daily demand forecasting dataset. Here are some important results and comparisons between uh, the different algorithms. Here we can see that robust variable forgetting factors produces the least amount of error, whereas the kernel recursive least squares produces the most mean absolute error. Similarly, the mean squared error for KRLS is relatively higher than the other algorithms, and so is the explained variance score. Conclusions. We could see that the kernel recursive least squares algorithm produces the most error and variance score compared to all the other algorithms. Robust variable recursive least squares algorithm produces the best results as it takes advantage of both adaptive and locally weighted algorithms and adjusts the forgetting factors to produce the best results. The variance score of the algorithm is close to 1.0, indicating the better squares of standard deviations of the errors. By adopting these algorithms, one can deal with time varying and non-linearity issues simultaneously. Thank you.